This is Pre-Algebra Lesson Chapter 4.1, Factors and Prime Factorization. In 6th grade math, you learned to write prime factorizations. This year we're going to apply that information in a new way. I'll show you how that works with our first example. You're working on your school yearbook. Each page will have 24 student photos. The photos will be arranged in a rectangular display with the same number of photos in each row. How many ways can you arrange the photos so that there are no more than 10 photos in any row or column? We can use factors to determine the number of possible displays. For the yearbook we've described in the question above, each possible display will consist of 24 photos. Because there will be the same number of photos in each row, the number of photos in each row will have to be a factor of 24. So let's begin by writing 24 as a product of two whole numbers in all possible ways. In other words, let's factor 24. So we begin with 1. We know 1 is a factor of 24 because 1 times 24 equals 24. Moving up number by number, let's go to 2. 2 also fits equally into 24. It goes in 12 times. 3 is also a factor of 24. 3 times 8 is 24. 4 is a factor of 24. 4 times 6 is 24. We know we're finished because these two numbers times one another equal the number we're factoring. So here is our list of factors. 1, 2, 3, 4, 6, 8, 12, and 24. All right, now that we know the factors, we can use the factors to find all of the possible rectangular displays with no more than 10 photos in any row or column. All right, if we can't have more than 10 photos in the any row or column, we know that 24 and 12 are out, right? Therefore, 1 and 2 are also out. So now we simply lay out all of our possibilities. We can have 3 rows of 8 photos. We could have 8 rows of 3 photos. We could have 4 rows of 6 photos, or 6 rows of 4 photos. So there are 4 possible ways that we can display the pictures. Now practice factoring on your own. Please write all of the factors in each number in problems 1 through 4. So write all of the factors of 30, of 31, of 45, and of 87. When you come back, we'll talk about prime and composite numbers. Before we move on to prime factorization, let's review a couple of key vocabulary terms. A prime number is a whole number that is greater than 1 and has exactly 2 whole number factors, 1 and itself. For example, 31 from our previous problem is prime. It only has 2 factors, 1 and 31. A composite number is a whole number that is greater than 1 and has more than 2 whole number factors. For example, the number 4 is a composite number because it consists of the factors 1, 2, and 4. The number 1 is a lone guy. It's neither prime nor composite. 1 is just 1. 1 cannot be a prime number because it only has a single factor. Now let's practice prime factorization. When you write a number as a product of prime numbers, you're writing its prime factorization. You can use a diagram called a factor tree to write prime factorizations of a number. Let's begin with this example, 630. One possible factor tree for 630 is to write 30 and 21. We know 30 and 21 multiplied by one another give us 630. Now we factor 30 as 5 and 6, and 21 as 3 and 7. 7 is already prime, so we're simply going to drop that down. 3 is also prime, so we're simply going to drop that down. 6 has two factors, 2 and 3, which are both prime, so we're done with 6. And 5 is already prime, so we simply drop that down. So we would write this now as 630 equals 2 times 3 times 3 times 5 times 7. That's the prime factorization. Let's write another possible factor tree. There's more than one possible way to find the prime factorization of 630. So let's follow another factor tree through. 630 is equal to 63 times 10. 63 and 10 each also have factors other than 1 in themselves. They are not prime. 63 is 9 times 7. 10 is 2 times 5. 9 is not prime. We know we can split it again. 3 times 3. Both of these numbers are prime, so we're done factoring 9. 7 is prime, we simply drop it down. 2 is prime, we simply drop it down. 5 is prime, we simply drop it down. Now we write our prime factorization like this: 630 equals 2 times 3 times 3 times 5 times 7. Please note that you always write the factors in order from least to greatest value. Here's one last possible factor tree for 630. This factor tree will show you the way we learned how to do this in 6th grade math, so that you can call back on that memory as you're applying this new information. So 630, we would have started with 2. And 630 divided by 2 gives us what? 315. Now remember, we just carry this 2 along so we don't forget about it. 315 is not divisible by 2, so let's try 3. It is divisible by 3, 105. Okay? Remember, we just carry these along so we don't forget about them. 105 divided by 3 gives us 35. Once again, carry these primes down so we don't lose them. 35 is divisible by 5 and 7. And there is our prime factorization. So we can actually write this one almost like this: 630 equals 2 times 3 times 3 times 5 times 7. You just drop each number down, and there's your prime factorization. You can use whichever way works best for your brain. I personally like to start with the least prime factor, so I usually start with 2 or 3, just because that's the way my brain likes to do it. If you prefer starting with 2 larger numbers and splitting them apart as you go, that's absolutely fine. Just show me your work so I understand your thinking. Try these next 8 problems on your own. First, indicate whether each number is prime or composite. If the number is composite, write its prime factorization. Go. And here's our last idea for Chapter 4.1. We're going to factor monomials. A monomial is a number, a variable, or a product of a number and one or more variables raised to a whole number power. For example, 7x is a monomial. It's a number times a variable. As a comparison, 7 plus x, not a monomial, because we're getting a sum, not a product. If it's a monomial, we need to be getting a product, 7 times x, not 7 plus x. Another monomial is 25 times m times n squared. We have a number, a variable, and a variable raised to a whole number exponent. That is a monomial. However, 25m minus n squared, not a monomial. We're finding a difference, not a sum. Another example of a monomial would be 24 y cubed z squared. We have a number times a variable raised to a power times another variable raised to a whole number power. That's a monomial. However, 24 plus y cubed plus z squared is not a monomial because we're finding a sum, we're not finding a product. Now that you see the difference between the two, let's go on to finding the factors of a monomial. Okay, let's factor this monomial, 28xy cubed. Okay, so what is in 28xy cubed? Let's find all the individual elements. We have a number, 28. We have a variable, x. And we have a variable, y cubed. The first thing we know we can split up is the y cubed, right? Y cubed is simply y times y times y. So now we've factored that element. We can also factor 28. We can find the prime factorization of 28. So I'm just going to move over here quickly, make a factor tree. 2, 14, 2, 2, 7. Oh, look at that. That was quick and easy. So now we can rewrite 28 as 2 times 2 times 7 times x times y times y times y. Voila! We have factored our monomial. All we've done is take all the individual pieces, all the individual factors, and represented them independently. Just like you're doing with a prime factor, except in this case you have variables involved. Here's your final checkpoint for this chapter. Please factor each of these monomials. I'll see you tomorrow and we'll practice more factoring with prime and composite numbers as well as monomials.